Right, how's everyone doing? Okay, hopefully you guys are doing well with circles. All right, hopefully we're catching on to everything we need to learn about circles. Circles are very complex. Again, if you guys ever have any questions, feel free to ask. I mean, I know my pre-calculus right now is doing some pretty hard things in their course, and I told them to ask away. They've been sending me a bunch of questions, and I respond with some answers. So if you guys ever feel like you need to do that, please do that. If you're not understanding something, please reach out. Don't just wait until it comes time for the exam that you don't know what you're doing. Okay, I know it's hard that you're learning at home by yourself. With no real instruction, no feedback from me. But it is, we can try to make the best of it. So again, if you have any questions, just please ask me. Don't hold out. All right, so we're going to talk a lot about chords and their different properties in this section. Okay, so as just a reminder here, okay, a chord is a segment that intersects the circle at two locations. Okay, so here we have a chord that separates the two arcs into a major arc and a minor arc, and then diameter is also considered a chord. But the diameter actually goes through the center of the circle. And the diameter is going to break up the arcs into two semicircles, all right? Okay, so here's our first theorem. Okay, it says in the same circle or incongruent circles, two minor arcs are congruent if and only if the corresponding chords are also congruent. Okay, so here, if you look at the image, we have segment AB is congruent to segment CD. So because those two chords are congruent and they're in the same circle, then this arc here, AB, is going to be congruent to this arc here, CD. Okay? And that works vice versa as well, right? So let's say instead we had the information that these arcs were congruent. If those arcs are congruent, then the two chords will also be congruent. Okay, so they work hand in hand. And that's one of the first theorems that we have. The idea usually, you can prove it using right triangles. So that's kind of where they're coming from. All right, and we're going to kind of do a little bit with some more right triangles within these circles moving forward. All right, so that's the first one. If you see congruent chords in the circle, then the arc's also going to be congruent, right? So if you kind of take a look at the diameter, right? So we have one segment here. The diameter is congruent to itself. It's reflexive, right? So the property still applies, right? So the arcs that are opposite of the diameter are going to be congruent. So there you have the two semicircles, the two arcs being congruent, okay? All right, so let's move on to the next section. Okay, so use the diagram of the circle D. Question 1, if the measurement of arc AB is 110 degrees, find the measurement of arc BC. Okay, so this is going to be, 110. Okay, and we are looking for the measurement of arc BC. Okay, so as we work through this, AB is 9, the chord BC is also 9, so I know they're congruent, okay? So since these two chords are congruent in the same circle, I know that their arcs also need to be congruent, okay? So this should also be 110, okay? So the measurement of arc BC is going to be 110 degrees, okay? All right, so let's look at example 2. All right, so it says the measurement of arc AC is 150. All right, so now we have to think, right? We have to pay attention to the arc and how it's labeled. AC is 150. So there's kind of two options for AC. It's either going to be the major arc here or it's going to be the minor arc. Now, which of the two arcs do you think it's going to be? It is going to be the minor arc because it is less than 180 degrees, which is the semicircle. Okay, so 150 is here. Okay, and we are looking for the arc of AB. We're looking for this arc here. All right, so how do we find that? Well, again, I know that this two here are congruent. I don't know the measurement of arc AB, right? But I know whatever the measurement of arc AB, let's call it X, is also going to be the same measurement of arc BC, okay? So how can we set up an equation or a model to help us solve this? Well, that's going to be X plus x plus 150 needs to equal how many degrees? And that's going to be 360. Okay, so we're going to find this sum. So 2x plus 150 equals 360. 2x is going to be equal to 210. X is going to be equal to 105. Okay, so therefore the measurement of arc AB is going to be 105 degrees. Okay, all right, awesome. Okay, again, if you have any questions on that, just let me know. You know, we can go over that. There's no issue. Let's move on to the next slide. Okay, so a lot of just more information that you're going to have to know. Okay, so the first part is bisecting arcs. Okay, so here, let's read it. It said if arc XY is congruent to arc YZ, then point Y and any line, segment, array that contains Y is going to bisect arc XYZ. All right, so just notice that since these two arcs are congruent, this is acting as a bisector that's cutting it into two congruent arcs. Okay, so it just works the same way as angle bisector, segment bisector. All right, but now we're just working at a segment array or line that is going to bisect an arc. Okay, so it has the same properties as the other ones. It's just splitting it up into two congruent arcs. All right, so the first theorem here, if one chord is a perpendicular bisector of another chord, then the first chord must be a diameter. Okay, so look at the case here, right? We see that SQ is bisecting TR, and it is also perpendicular. It's a perpendicular bisector, right? So therefore, SQ, the center is going to be somewhere on the segment SQ, somewhere on there, all right? SQ will be the diameter at that point, okay? Now, the idea behind this, okay, the idea behind this comes, if I gotta zoom in a little bit here, okay, that you're going to have a center point here, okay, and notice that the radius can be drawn here and the radius can be drawn here, right? So what are you kind of creating here? You're kind of creating an isosceles triangle, right? Because this length is R for the radius, whatever the radius is, and this length is also R. Now, those two segments are going to be congruent. You have these two segments congruent, all right? So that already gives you a hypotenuse and a leg, and then notice it's a right triangle. So therefore, those two triangles are going to be congruent. So it's very important to know that the vertex of the triangle we're creating here is the center point of the circle. And R is considered the radius of the circle. Now, this little technique of always drawing the radius is actually going to be very important for a lot of questions when you start getting into more complex ones. Because if you draw the radius, any radius of any circle, you're going to create two congruent segments automatically. So now that could help you a lot when you're especially working with triangles, okay? All right, so that's just some information that's good to know and how we get there, okay? And the second one here is if a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. Okay, so basically what it's saying, okay, is kind of like the converse in a sense. So you have the center here. It's perpendicular to the chord, so now I know that these two segments are going to be congruent, and if those two parts are going to be congruent, then it's also going to cut these two arcs into congruent pieces, okay? So it kind of works hand in hand. So here, same idea, these two arcs would be congruent because it's perpendicular, and you're splitting up that chord into two congruent parts, therefore those two pieces of the arc will also be congruent, okay? So it's kind of like the idea of, since it's being bisected, not only is the chord going to get bisected, but also the arc is going to get bisected. Okay, so let's look at some examples on the next page here. All right, so we're looking for the measurement of arc CD, okay? So we're looking for this measurement here, the representation of 9x. All right, so if I'm looking for 9x, I notice here that BD is a diameter, and the diameter is intersecting segment CE at a perpendicular line, right? So these two are perpendicular. Because they're perpendicular, I now know that this segment is going to be congruent. Let's actually do that in a color red. This segment's congruent to this segment. Okay, if those two segments are congruent, then I know that these two arcs are also congruent. So let's set up an equation to solve that. So we have 9x equals 80 minus x. 10x is equal to 80. X is equal to 8. All right. Now x is equal to 8. That doesn't give us the measurement of the angle of the arc. So 8 times 9 is going to be 72. So the arc measurement is 72 degrees. All right. So let's look at a second example here. Arc DE. Okay. So arc DE. Now we kind of did the work of the bulk load or the work here. We know x is 8. So 80 minus x, 80 minus 8 is going to be equal to 72. Now, if you got the answer right away without having to really think about it, that's because you know the property that CD, the arc, is already congruent to DE. So whatever this angle was, or this measurement was, this measurement should be the same thing, right? Because we know that they're congruent. All right, and then CE altogether, all right, well, again, it's kind of obvious here. CE arc makes up both CD and DE, so you can just add the two arcs. So that's going to give you 144, okay? Again, you're using arc addition postulate or arc addition properties there, okay? All right, good. Okay, this theorem here, in the same circle or in congruent circles, two chords are congruent if and only if they're equidistant from the center. Okay, now, if you guys remember when we talked about distance, right? The way we measure distance is usually by using a perpendicular line to a segment. So we're looking here at the center. The center is perpendicular, or this little chord, this little segment here. Let me highlight that. This little segment here, right, is perpendicular to the chord. So that's you're finding the distance from the center to the chord. Now notice, if it's perpendicular in the same circle, then what I know for a fact is that these two chords, okay, so AB and CD are going to be congruent to each other, okay? All right, now let me show you exactly how we prove this so that way you guys can see exactly why this is the case, right? So let's go back a little bit. Okay, then I'm going to zoom in just to kind of get a better drawing picture here. All right, so again, if I draw the radius for these triangles, okay, what am I doing here? I have R, 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 and R. So all these are congruent, right? So we have that much information in terms of the triangle, okay? We just need another kind of piece, right? Well, I know that they're equidistant, so this segment is congruent to this segment, right? So that gives me, again, a hypotenuse and a leg for these right triangles. So if I have hypotenuse and leg in a right triangle, that means that this right triangle is congruent to this right triangle. And since these are just isosceles, then these are also congruent as well. Okay, so all four of these right triangles are congruent. So if all four right triangles are congruent, then I know that this chord is congruent to this chord, right? So that was the goal of the theorem, is to show that the two chords are congruent. Okay. Now, if those two chords are congruent, then what do we also know about the arcs? These arcs are also going to be congruent. So that, again, a lot of powerful things are done just because we use the radius and we draw the radius, right? So it's a very important theme, is that the radius of the triangle of the circles within the same circle or congruent circles are always going to be congruent. Okay, all right, so let's look at this example here. In the diagram of circle P, it says the length of PV is equal to the length of PW. So they already marked that for us. They told us that they're congruent. All right, so the length of QR is 2x plus 6, and the length of ST is 3x minus 1. Find QR. Okay, so again, since these two are congruent, and I know that this is my radius and this is my radius, okay, those two radius, they're congruent. That creates an HL theorem, which tells me that the entire segment QR is going to be congruent to the entire segment ST. So if they're congruent, then 2x plus 6 equals 3x minus 1. All right, and then we start solving the process. So we get 2x plus 7 equals 3x. 7 is equal to x. So x is 7, but again, they're looking for QR. So QR is going to be equal to 2 times 7 plus 6, and that gives us 20. All right, so the length of QR is 20. Okay, so hopefully this works out. Again, chords are powerful, especially in triangles, because chords go well with the radius. And again, using the radius is a very powerful tool. Okay, so again, if you guys have any questions, please ask. Do not be afraid to hesitate. Okay, I'm sure a lot of you have had questions so far, but no one's really sharing. So if you share, I'm sure everyone else will follow suit. So someone just needs to be bold enough to ask the first question. All right. Hopefully you guys are doing well with this. I'll see you guys soon, hopefully. But there you go. There's section 10.3, applying the properties of circles. Okay. Thank you.